Everyone, in previous lecture we have seen the concept for sway type of portal frame which are to be used in moment distribution method. In that we have seen the relative stiffness coefficients how you have to take, that is I by L square value how we have to conduct, that we have seen. Now in today's lecture we'll start with the numericals, but before that we'll see some theoretical part which is to be taken or considered in your moment distribution method. So I am writing the heading here, moment distribution method for sway type of portal frame. For sway type of portal frame. Now sway frame means what? Which sways due to the wind or earthquake effects over there, or in which swaying effect delta occurs over there. That type of frame is called as your sway type of portal frame. Okay. Now in analysis of moment distribution method, the first initial step whatever you have to do is you have to assume that your frame doesn't sway. What you have to do is you have to assume that frame doesn't sway over there. That frame does not sway. Okay, and whatever analysis you will be carrying out, that is the calculation of distribution factors, after that calculation of moment distribution table, whatever the analysis you will carry out by taking this assumption, that analysis will be called as your non-sway analysis. That analysis will be called as your non-sway analysis, and whatever moments you will get in this non-sway analysis in moment distribution table, those moments will be called as your NSM, that is nothing but non-sway moments. Okay, now after this what you have to do is that, suppose I am considering any frame over here. Due to this lateral load, what happens? It is a swaying with an amount total displacement, suppose delta over here. Okay, so in second step what you have to do, you have to apply the corrections for the swaying of the frame, that is you have to apply the correction displacement equal to delta over there. Okay, this will be your total displacement, and this is the just displacement which we are considering in your sway coefficients over there. Okay, while calculating the sway moments over there. So again, by using your relative stiffness factor, that is I by L square, depending on the support conditions over there, you have to calculate the ratios of moments MBA is to MCD over there, and remaining moments you have to carry out as I have explained you in the previous cases over there. And again analysis you have to carry out, that is again moment distribution table you have to carry out, and that analysis will be called as your sway moments analysis, or you directly called as sway analysis over there. So whatever this correction will be applied for this moment, that will be suppose X. From that we have to calculate the total actual displacement, that will be a step number 3, that is total actual displacement you have to calculate from this by applying, that is for delta is X times the assumed sway. Total actual displacement delta is X times the assumed sway, that is nothing but delta over there. That means your complete this capital delta will be equal to X times of small delta over there. And using this two analysis, that is you have to combine these two analysis. First is your non-sway analysis, and after applying this correction over there, you have to combine the non-sway and sway analysis from this, and finally you have to calculate the total final moments. Total final moments is equal to, that is nothing but NSM non-sway moments plus X times of whatever moments will be obtaining here in sway analysis, that will be called as your actual sway moment. So that will be X multiplied by ASM. So using this formula you have to calculate the values of final moments. Likewise in previous lectures what we have done, in case of beams and non-sway frame, directly whatever last moments we are getting, those were your final moments, or your final moments were nothing but non-sway moments over there. But here due to swaying effect, your actual sway moments are increasing over there. So you have to do this stepwise performance over there. That is, in first step what you have to do, you have to consider that frame doesn't sway, and analysis you have to carry out, moment distribution table you have to do. That analysis will be called as your non-sway analysis, and moments obtained there will be your non-sway moments over there. Okay, after that you have to assume the swaying coefficient delta, and again you have to carry out the analysis using the relative stiffness factors over there, and that analysis will be called as your sway analysis. In that correction X will be applied, that correction you have to apply to the total displacement over there, and at last you have to obtain the final moments, which is equal to non-sway moments plus x times of actual sway moments over there. Okay, so using this concept you have to carry out the sway analysis for moment distribution method over there. Okay, now we'll see one numerical on this so that you will clearly understand for how you have to carry out the analysis of moment distribution method over there. Okay. Okay, so this numerical we'll see, that is you have to analyze this frame, sway frame, it is by using moment distribution method. That is you have to find out the final moments in this frame over there. Okay, now how this frame will be classified as your sway frame, that is if you differentiate it in between over there, your left hand side and right hand side part is completely different over there. That is one thing. Again, due to this lateral load of 50 kilonewton, it will emerge some loading on this column AB and column CD over there. That is, we assume that your swaying at point B and swaying at point C is same. That is, delta at point B and delta at point C will remain same over there. Okay, so initially what you have to do, you have to repeat your same steps again. So we'll start with the solution here. Solution, what you have to do is the first step, you calculate the degree of kinematic indeterminacy, that is decay. So decay for this frame will be here theta A, theta B and theta C, and along with that you have to carry out is the delta. So total decay you are getting here equal to 4 over there, theta A, theta B, theta C, and 1 is your delta over there. But we do not deal with mostly with decay value in your moment distribution table, so it is okay. Number more than 3 unknowns also you can solve that numericals by using moment distribution method very easily. Okay, so directly what we'll do, we'll carry out the fixed end moments over there. So second step is to carry out the fixed end moments over there. Okay, so fixed end moment for first member we'll see MFAB. In span AB, a loading is there, point load at non-uniform distance, so that will come equal to minus WAB square divided by L square. So if you calculate this, you will get this as minus 9.375 kilonewton meter. Next, MFBA. In MFBA, you will get plus WA square B divided by L square. So W is 50, A 3, B will be 1 divided by L is 4. So total length if you substitute, you get this as 28.125 kilonewton meter. After that, MFBC is equal to minus of MFCB. So that will be your minus WL square divided by 12. I have written combine this by, because restoring sign of BC and CB will be opposite to each other. So if this comes negative, this will come positive over there by cancelling the negative signs over here. Okay, so W, that is 2.5, length of is BC is 5 square divided by 12. So that comes here equal to minus 5.208. Okay, and then in last member, that is CD, there is no any loading given, so MFCD and MFDC will remain completely equal to 0 over there because there is no any loading given there. Okay, so this will be our second step. That is, you have to calculate the fixed end moments. We have calculated this many times, so I don't think any problem will be there for calculating fixed end moments over there. Next, you will be calculating the distribution factors over there. That is, first 3 steps whatever you are going to do, those are same as your non-sway analysis moments over there. Okay, so in this distribution factor, first column what you do is the joints, next is the members meeting these joints, next relative stiffness K, after that total stiffness summation of K, and last is DF is equal to K divided by summation of K. Okay, now while considering these joints over there, which joints you have to consider here? I have told you many times, that is joints such you have to consider at which 2 or more than 2 members are meeting over there, because for single jointed members here DF will be always equal to 1. Okay, so such joints are 2 in numbers, that is joint B is having more than 2 members and joint C is also having 2 or more than 2 members. So first joint what I will be treating, that will be your joint B. Okay, from joint B, members meeting joint B are BA and BC. Okay, so your farther end will be A and C. We'll check the capability of the supports A and C. A, that is the hinge support, so this type of support will be your incapable support, while as your C is nothing but a rigid joint, so that type of support will be called as your capable support over there. Okay, so relative stiffness, whatever you are going to calculate for B to A is your incapable support, so relative stiffness comes here equal to 3/4 of I by L. Now if you see, I value is given to you directly, I here. Okay, so it will remain as it is. Length of member BA, that is equal to 4. So I'll write here 4. So this comes equal to 3I divided by 16. So if you simplify this, I get this value is equal to 0.18 of I. You check this value, I'm getting as 0.18 of I over there. Okay, now in next member B to C moment is getting transferred, so C will be your farther end, that is nothing but a capable support. So for capable support, your relative stiffness comes against equal to I by L. L of BC is 5 and I value is given to I over there. So I by 5, that comes again equal to 0.2 of I. Okay, here total stiffness will come 0.18 plus 0.2, that comes equal to 0.38 of I. Okay, so if you calculate DF for this BA member, it will be K divided by summation of K, that is 0.18 by 0.38. You will get this as 0.48. I will get cancelled over there, and this will come 0.2 divided by 0.38, that comes equal to 0.52 over there. Summation that shall come equal to 1 at a particular joint. Okay, then next joint I will conduct, that is joint number C. So members meeting joints here CB and CD. Okay, so farther end is your B and D. Will check capability of those members. So B is nothing but a rigid joint, so that type of support is again called as your capable support. Okay, and D is the fixed support. Fixed support is also called as the capable support over there. So at for both the members, your relative stiffness will be I by L over there. So we'll see one by one. CB member, so for B, relative stiffness comes equal to I by L. L of CB is again 5. So I by 5, I get this as equal to 0.2 of I over there. Right. Next, moment is transferred from C to D. D is again your capable support. So for capable support, again relative stiffness comes I by L. L of member CD is your 4. But here change is what? Your I value is given to equal to 2I. So that becomes 2I divided by 4. That is I by 2. It comes equal to 0.5 of I over there. So if you add this for total stiffness, 0.2 plus 0.5, I get equal to 0.7 I, and DF for first member CB, 0.2 by 0.7, I get equal to 0.28, and here 0.5 by 0.7, I get almost equal to 0.72, whereas summation of this shall come equal to 1, and again this shall come equal to 1 over there. So that gives me the distribution factors over there for joint B and joint C members. Okay, now change in the next step is what? Is your moment distribution table over there. That moment distribution table also you have to keep same as it is. Just I am changing the name of this step. That is what I am doing is the non-sway analysis. In this what we'll do? We assume that your initially frame doesn't sways over there. Initially we assume that your frame doesn't sways over there. Okay, I'll not have sufficient space for this, so I'll change the paper over here. I'll write over here. Okay, so your next step number 4 is the non-sway analysis. Whatever moments will be obtaining in this table, that will be called as your non-sway moments over there. Okay, so for non-sway analysis, again same moment with distribution table you have to carry out. Here you can write assuming that frame does not sway. Assuming that frame does not sway over there. So here your first row is what? Joints. Next is your members meeting these joints. After that distribution factors, and then fixed end moment. So these 4 rows remains common for every table over there. Okay, so for joints, your first joint is A, second B, third joint is C, and last joint is your D over there. So in this you have to consider all the joints which you are having in complete frame over there. Okay, so members meeting joint A are AB, members meeting joint B are BA and BC. Here you are having CB and CD, and last members meeting joint D are DC over there. Distribution factors that we have calculated over here, right? So distribution factor for BA, BC, CB and CD we have calculated. I'll write that over here. For BA, I've got that as 0.48. BC I am getting 0.52. For CB I am having 0.28, and for CD I am having 0.72 over there. Okay, so these are my distribution factors here. Then I'll write out the friction moments which I have got over there. Friction moment for MFAB, that is minus 9.375. Next for BA I am getting 28.125, that is positive. Next minus 5.208, here I am having plus 5.208. For CD and DC there was no loading, so that moments came 0 over there. Okay, now after this what you have to do is you have to apply the balancing moment over there, where at your incapable support first. So we are having any incapable support? Yes, we are having, that is your support at point A over there. So what you have to do, you have to apply the balance moment, that is you have to make the moment at joint A equal to 0 over there. So initially moment we are having there friction moment minus 9.375, so balancing moment that we get plus 9.375, out of which half of the moment will get carried out to its next capable support, that is support B over there, that is AB moment will get carried out to BA. So half of 9.375, that comes equal to plus 4.68 over there. Okay, and here this will be your carrier. So whatever values you will get here, those will be your initial moments over there. Okay, so I'll write that initial moments. So for first AB I am getting 0, 28.125 plus 4.68, I get this almost plus 32.80. Next minus 5.208 is as it is plus 5.208, and these remaining moments are 0 directly. Okay, now after calculating initial moments, what is the thing? You have to do the distribution of moments, for which you have calculated distribution factors over there. Okay, so for distribution factors you have to distribute moments along joint B and joint C over there. So here summation of this 32.80 minus 5.208, something 27 point you will get, multiplied by distribution factor 0.48 and 0.52. So whatever summation you get here, that will be positive. Distribution is to be done by opposite sign, that is negative. So distribution for your joint B members will be negative. So summation of these two multiplied by 0.48, I get this almost equal to 13.24, and here I get almost equal to 14.35 over there. Okay, same way distribution of these two moments plus 5.208 plus 0 you are having, so distribution is positive here, sorry, summation is positive over here. So that summation multiplied by 0.28 and 0.722 gives me opposite distribution sign, that is minus 1.46 and minus 3.75 over there. Okay, distribution is to be done with opposite sign, always remember. After doing the distribution, next is the carrier of which moments you have to do, for which you have calculated distribution factors over there, or which you have distributed further. Now this carrier is not possible over there, because why? Your joint A is the incapable joint, so this carrier is not possible. What will get carrier? BC moment will get carrier to CB, and CB moment will get carrier to BC over there, and CD moment will get carrier to DC, because why? Your joint D is your capable here, B and C is also capable here. Only carrier towards A is not possible, because A is the incapable support over here. Okay, so carrier factor is your 1/2, so half of this 1.14.35, that comes equal to minus 7.175, right? Next half of 1.46, that comes almost equal to minus 0.73, carrier is to be done with same sign, and then minus of 3.75 divided by 2, that comes almost equal to 1.875. Okay, now here your moments are remaining, that is here 0 and here also 0, so your cycle will get repeated again. So next is again you have to do the distribution. So 0 minus 0.73, summation is minus 0.73 multiplied by these distribution factors, so I get this almost equal to, now this is your summation is negative, so distribution will come positive, so I get this 0.35, and this I get as 0.38. 0.73 into 0.48 is 0.35, 0.73 into 0.52 is 0.38. Same way you have to distribute this minus 7.175 to this distribution factors over there, so summation is negative, distribution will be again positive for both. So 7.175 into 0.28, that comes almost equal to 2, and 7.175 into 0.72, that comes almost equal to 5.15. 6. You check these values here, some decimals may get just shift over there. Okay, next is the again same cycle, carry over you have to repeat. So this carry over is not possible. BC moment will get carry over to CB, CB will get carry over to BC, and CD will get carry over to DC over there. So half of this carry over factor is again 1 half. So 0.38 divided by 2, I get this as plus 0.19. Half of 2 that comes equal to 1, and half of 5.166 that comes equal to plus 2.583 over there. Okay, now almost answers I am not getting in 0 point. So again one more cycle I will repeat, that is I will do the distribution of moments again. Okay, so here again 0 I am having, here also I am having 0. So these two moments you have to distribute now. So 1 into these distribution factors and 0.19 into this distribution factor over there. So 1 into 0.48, I get that almost minus of 0.48. Minus why? Because this summation is coming positive over there, and this I will get as minus of 0.52. Next 0.19 into 0.28, again this is your positive, so distribution will be again negative for both. So 0.19 into 0.28 over there, I get this almost minus 0.05. okay, and this I am getting as minus 0.14 over there. Okay, now what I will do, again I am answers I am not getting almost in 0.0 something. So one more cycle I will repeat, that is your carry over there. So this carry over is not possible, these two are possible, and this is also possible. So half of 0.05 I get that as minus 0.025. okay, next half of 0.52 I get that as minus 0.26, and half of 0.14 I get as minus 0.07 over there. Okay, I have told you in your previous lectures that where you have to stop the table. You have to stop the table after doing the distribution over there. Okay, where if you stop the table at the carry over, your moments will not get matched over there. That is for conditions of equilibrium, your values will not get correct. So where you have to stop the table after doing the distribution. So distribution of again these moments. Okay, so 0.025 into your distribution factors 0.48 and 0.52 over there. Now this summation is negative over there, so distribution will come again positive. Okay, so this comes 0.025 into 0.48, I get this as 0.012, and this I get as 0.013 over there. Okay, same way distribution of minus 0.26 will be again positive, so this will come 0.07, and this comes equal to 0.18 over there. Now here you can stop the table over there. So whatever values I will get here, those will be your final moments over there, but we will call that moments as your NSM, that is nothing but non-sway moments over there. Okay, so summation of this you get 0, summation of this I am getting at equal to 19.44, this I am getting as minus 19.44. you check these values over there, this I get as minus 1.47, this I am getting as plus 1.47, and this I am getting as plus 0.638 over there. This is your non-sway moments, that is MAB, this is your MBA, BC, MCB, MCD, and this last is your MDC over there. So this analysis you have to carry out, that is the non-sway analysis over there, that is your same as your previous numericals. Okay, now we'll proceed to your next step, that is step number 5 over there. So step number 5, that will be your sway analysis. Step number 5 will be your sway analysis. In non-sway analysis, what you have done, we are assume that frame is not swaying over there. Here we'll assume that your frame sways now. Assuming frame sway with displacement delta over there, So here what you have to do is that you have to calculate the ratio of initial moments over there, that is relative stiffness coefficients you have to calculate. So right here, ratio of initial moments, so which are those? MBA is to MCD over there. Now if you see in this numerical, you are having one end is your hinged over there and second end is your fixed over there. That is, you are using the case number, you have to use the case number 3 over there. So for case number 3, what relation you will get? That is I1 divided by L1 square is to 2I2 divided by L2 square over there. Okay, for that you can refer your previous lecture over there, where your hinge is having at that end your value comes 1, and where your fixed end is there, at that end your value comes equal to twice over there. So this ratio I get as I1 by L1 square is to 2I2 by L2 square. So I'll substitute the values over here. That is I for your BA member is given to you. Okay, so this is for BA member, your I value is given to you I, and for this it is given to you equal to 2I over there. So I'll substitute that. So this I get as I1 divided by length of your BA is 4 square, right, is to, here I am getting as 2 of I divided by 2 of 2I. So that will become 2 into 2, 4I. So 4I divided by again 4 square over there. So this ratio I will get as I by 4 square will get cancelled. So this ratio remains to 1:4 over there. So moment for BA I am getting in ratio of 1, and moment for CD I am getting in ratio of 4 over there. So ratio I am getting equal to 1:4. Now I will find out the final moments over there for this. So the first moment whatever I am obtaining, that will be your MAB, that shall be equal to 0. Why? Because A is the incapable support. So your whatever moment you are obtaining here, MBA will not be equal to MAB, and it will be 0, right? Next, MBA moment, that I am getting how much? It is equal to 1. But in considering your friction moments table over there, what we do, we consider the restoring signs. So always apply here opposite nature, that is -1 over there. Okay, because why? If you consider this as your frame over there, and whatever moments you apply here due to translational displacement delta over here, whatever these values come, these values comes equal to, clockwise we consider those as negative, anti-clockwise this comes as positive over there, but we consider restoring signs over there, so that is why we consider here -1 over here. Okay, because both direction of this is anti-clockwise in nature. Next, MBA is happening. Now for horizontal member, that is MBC and MCB, your moment remains 0, and next your MCD and MDC will remain equal to -4 over there. This ratio will come over here, and here DC is your capable support. That is why, because your MCD and MDC values are remaining same. If D is your incapable support, then this condition will come as your first AB member over there. Okay, so these moments I am getting here. Now using these moments, again you have to carry out is the moment distribution table over there. Okay, so for again here I'll write as joints, next is the members, okay, then next is the distribution factors, and last is the friction moments over there. Friction moments, which one? What are these new moments we are obtaining? So joints are again your A, B, C and D. Then members meeting joint here AB, here BA, BC, CB, CD, and here is DC over there. Okay, so distribution factors again same we have writing over here 0.48 and 0.52, and here I have got 0.28 and 0.72 over here. Okay, now here friction moment values I'll write. AB I am having 0, BA I am having -1, BC and CB I am having both again 0, and CD and DC I am having as -4 and -4. Now the thing is what, here you do not apply any balance moment over there, because why? At your incapable support already moment is coming equal to 0 over there, so no need of applying any balancing moment over there. That while calculating this initial moment, that is why this name is given to its initial moments over there. So while writing only, it comes directly equal to 0, so no need of applying any balancing moment over there. Directly we will carry out the distribution over there. So next is the distribution. So come on, so -1 summation, this will come equal to -1, so next distribution will be positive, so this will come as 0.48 and this will come as 0.52. Same way this summation comes 0 -4 as -4, so -4 into 0.28, again distribution will be positive over here, so that will come 1.12, and this comes equal to 2.88. Now distribution After distribution, we will do the carrier. For carrier, this carrier is not possible because A is your incapable support. BC will get carrier to CB, CB will get carrier to BC, and CD will get carrier to DC over there. Carrier factor is again 1/2. So half of 0.52 that I get as 0.26, and half of 1.12 I get as 0.56. Half of 2.88 I get as 1.44. Okay. Again, we'll repeat one more cycle for this. That is, we'll carry out the distribution again. Okay. So distribution of this moment, and here this moment you have to distribute again. So 0.56 into 48 and 0.52. So this is your positive here. So distribution will come again negative. Okay. So this comes equal to 0.27 and 0.29. Again, distribution of 0.26 for the distribution factor, that will come negative because this is summation is positive here. So 0.26 into 0.28 and 0.26 into 0.72, I get this as 0.07, and this I am getting as 0.18 over there. I'll do the carrier for this. This is not possible. This will get carrier to CB, BC will get carrier to, okay. So half of 0.29, I get this as minus 0.145. This I am getting as minus 0.035. This I am getting as minus 0.09. Okay. Now where you have to stop the table? After doing the distribution of moments over there. Okay. So distribution of moments. Again, here this moment you have to distribute. Here you are having 0. So this moment you have to distribute along the distribution factors over there. Same. You have to repeat again same cycles. So distribution will be again positive. So this I am getting as 0.016. This I am getting as 0.018, and here I will get as 0.04, and here I am getting as 0.104 over there. Distribution of 0.035 into 48 and 52, and 0.145 into 0.28 and 0.72. I am getting these values over there. Okay. So we'll stop the table here, because almost answers I am getting in very smaller values over there. Okay. So here whatever moments you'll get will be your sway moments, that I'll write as final moments, or you can write as ASM. That will be nothing but actual sway moments. Okay. So summation of this 0 will come as it is. Summation of this comes equal to minus 0.774. This comes as plus 0.774. This I am getting as plus 1.205. This I am getting as minus 1.205, and this I am getting as minus 2.65 over there. So these two tables you have to follow over here. Okay. Okay. So now one relation we have seen in our previous lecture over there, that is your final moments. Final moments is equal to non-sway moments plus x times of assumed sway or actual sway moments over there. Okay. So using this relation we will get relation for every member from these two tables over here. Okay. So we'll see that final moment, that is all members I'll write here, that is MAB, next is your MBA, BC, MCB, MCD, and last is your MDC over here. Okay. So non-sway moments, that will be your table number, table which you are calculated in non-sway analysis over there. So for this MBA I am getting equal to 0 plus x times of your assumed sway moment. So x into assumed sway moment from this table number 2, I am getting as 0, right. So for AB directly moment I am getting here equal to 0 over there. Okay. Next for BA non-sway moment I am getting as 19.44 here, right, plus x times of assumed sway moment, but here assumed sway moment is how much? 0.774, but that is negative, so I get this relation as minus 0.774 of x over there. Okay. After that again this BC I am getting as minus 19.44 plus 0.774 of x from assumed sway moments over there. Then next is your minus 1.47 plus 1.205 times of x. Next I am getting as plus 1.47 minus 1.205 times of x, and last is that I am getting at 0.638 minus 2.65 times of x over there. So these 5 relations I am getting here. Okay, from combining these two tables over there, you have to use this relation, final moments is equal to non-sway moments plus x times of assumed sway moments over there. Okay, so if you want to obtain the final moments over there, what you need to do is you have to find out the x value here. So for finding out x value, you have to do the shear equilibrium equation here. You have to carry out the shear equilibrium equation. So your next step increases here, that is your step number 6, shear equilibrium equation. Okay, so for shear equilibrium equation, what we do, we assume that the horizontal thrust for your body is towards the right over there. That is, you are having this frame over here. Okay, this frame you are having. So what I am doing initially, I am assuming that horizontal thrust HA and HD are acting towards the right over there. The same shear equilibrium equation step you have to repeat that we have done in slope deflection method over there. Okay, so assuming that step, what you do, using summation of fx relation, rightward forces positive is equal to 0, what I get as horizontal forces HA plus HD plus horizontal point load is given to you, that will be equal to 0. Here your UDL will be not considered because UDL is vertically downward acting. Okay, so this relation I will call it as A over there. Now you have to consider the column equilibriums in this. So for column equilibrium, in that you have to consider the first column AB. First column equilibrium diagram I will draw. Here I am having HD value over there. Sorry, HA I am having. This is my joint A. Here I am having B over there. Okay, along with that, here I am having 50 kilonewton point load at a distance of 1 meter from B and 3 meter from A over there. Initially what I do, I assume that my final moment at B is MBA and final moment at A is your MAB over there. I have to find out the value of HA. So using this equation, that is summation of moment at B is equal to 0, treating clockwise moments as positive. So what I will get as MAB plus MBA, right, minus 4 times of HA minus 50 will be equal to 0 over there. You have to take moment of all the forces along this. So MAB plus MBA minus moment of HA into distance 4 minus, since that moment will be anti-clockwise, and 50 into 1, that will come equal to 50 over there. So if I simplify this for HA, I get this as MAB plus MBA divided by 4 minus 50 divided by 4, that I get as 12.5 over there. Okay, here what I will do now, I am having the equations of MAB and MBA over there. These equations, MAB and MBA equation I am having. MAB is already 0, MBA I am having the equation. So you substitute that equation over here. So I get this as HA is equal to 19.44 plus 0.7 minus 0.774 divided by 4 minus 12.5 over there. Okay, so if you simplify this, I get this HA value as minus 0.194 of x minus 7.64 over there. 19.44 divided by 4 minus this 12.5 getting as minus 7.64, and 0.774 divided by 4, here I am having x multiplied to this into x, that I get as minus 0.194 of x. This will be my equation number B over there. Now second value I have to find out is the D over there. For that, what I need to do, I need to consider the equilibrium of column CD now. So I will consider the equilibrium of column CD here. Horizontal thrust is given to you, HD for this is your joint D, here C, moment here will be MCD, moment initially here will be your MDC. I have told you initially what you have to do, you have to assume these moments as clockwise in nature, and total length of this is your 4 over there. Okay, so HD relation what I will get here, MCD plus MDC divided by 4 directly. Okay, so I will substitute the MCD and DC values here. So MCD and DC, these two moment values I am having 1.47 minus 1.205 x, 0.638 minus 0.265 of x over there. So if I simplify this, I get this as divided by 4, I get directly value I will write here 0.527 minus 0.962 of x, or here you can write 1.47 minus 1.205 of x plus 0.638 minus 2.65 of x divided by 4. Okay, you simplify these common terms first. Divided by 4, I get this as 0.53527, and minus 1.205 minus 2.65 divided by 4, I get this as minus 9 point, I get this as 0.962 over there. This will be my equation number C. Now I will substitute this HA and HD value in this equation number A over there. So I get this as HA, I have got minus 194 of x minus 7.64 plus HD 0.527 minus 0.962 of x plus 50 is equal to 0. In this A equation I have substituted this HA and HD values over there. So if you simplify this, I'll get x value from this as x is equal to 37.09 over there. That is 0.94. Here I am not having x. 0.194 of x minus 0.962 of x, that will get simplified. Minus 7.64 plus 0.527 plus this 50 equal to 0. So from this I can calculate the value of x here, that I am getting as 37.09. So now what I'll do, I'll substitute this x value in this equations over there. What I'll get? I'll get the final moment values over there. So here I'll write those final moments over there after substituting of x over there. Final moments MAB, MBA, MBC, MCB, MCD, and last is your MDC. So MAB, directly I have got that value as 0. Next 19.44 minus 0.744 of x. X is your 37.09. So if you substitute that x, I get this value as minus 9.267, and all these values are in kilonewton meter over there. Next MBC, after substituting of x, I get this as plus 9.267. CB I am getting as plus 43.223, and DC I am getting as minus 43.223, and last value I am getting as minus 97.6 value. So all the moments I am getting here after calculating of x over there. Okay, from this now we can plot the bending moment diagram. Joint A, B, C and D over there. Our sign conventions we have for horizontal numbers negative, positive, positive and negative, and for vertical numbers negative, positive, positive and negative we have, right? So for AB you are having moment directly 0. Okay, for B I am having that as minus 9.267, so negative it is, so it will be plotted on inward side over there, that is somewhere here 9.267. join these two lines by a join these 2 points by a straight line over here. Next for BC member, here BC I am having as plus 9.20267 over there, so positive it is, so it will be plotted on downward side 9.267. here I am getting somewhere. Then for CB I am having that moment value equal to 43.223, positive it is, so it will be plotted on upward side. So again you have to join these 2 points by a straight line again. Now in member CD, for CD I am having this as minus 43.223, so negative, it will be plotted on outward side. And then for last DC it is minus 97, minus it is, so it will be plotted on inward side over there. So somewhere here I am not having more space, so you understand that just again join these two lines, 2 points by a straight line over there. Now I'll plot the span moments on this, maximum span moments. Okay, so span moment in CD will remain 0 because there is no loading given. So span moment in first member I'll calculate as MAB, and in second member I'll calculate as MBC. In MAB point load is given to you, so that comes equal to WAB divided by L over there. Okay, so if you calculate this, W is given to A is 3, B will be 1, so this comes equal to 37.5, and this comes equal to WL square divided by 8 because UDL is given to you. So for UDL this comes equal to 7.812 over there. Now in this, at the point of point load, this comes 37.5 somewhere here. 37.5, this is equal to WAB divided by L, and here this will follow parabolic path 7.812, that is WL square by 8 is equal to 7.812 over there. And just what you have to do is you have to shade the superimposed part here. Here there is no superimposed part, so no need of shading. And here you are not having any loading, so your maximum span moment there comes equal to 0. So, or you can write MCD will be directly equal to 0. So this will be your BMD by superposition. Okay, so this will be your numerical of sway frame by using moment distribution method of that. Numerical is actually lengthy because here mostly 2 steps are increased. Your sway analysis is increased 2 times. You have to carry out the moment distribution table, and your shear equilibrium equation is also increased over there. That is why your length of numerical is more longer over there. Okay, hope so you have understood it very properly. If you are having any queries, any problem from this, you can comment in the comment box. Thank you so much.